Hello everyone. Today we'll discuss the solution of gas dynamics and propulsion questions of GATE 2019 paper. So in GATE 2019, total contribution from propulsion and gas dynamics was of around 20 marks. And we will see the solution of all the questions in this video today. So the first question, it is said that for a quasi one-dimensional isentropic supersonic flow, so for a quasi one-dimensional isentropic supersonic flow through diverging duct, which of the following is true? So for a diverging duct, so this is the inlet of the diverging duct, this is the outlet of the diverging duct. And so the flow is isentropic, it's reversible adiabatic, and the incoming flow is supersonic. So we know from the area velocity relation for flow in a converging or diverging duct is dA by A equal to m square minus 1 du by u. Now for a diverging duct, dA, so for a diverging duct, dA is positive. So from this equation, and as m is greater than 1, hence this part will be greater than 0. So as dA is also greater than 0 for diverging duct, so du has to be greater than 0. Hence in a diverging duct, flow accelerates. So that means if the at the exit velocity is u2, the inlet is at u1, then u2 has to be greater than u1 for a supersonic flow in a diverging duct. Now as the flow inside the duct is reversible adiabatic, hence the total energy will be conserved in the duct, right? So the total energy at the inlet is CPT1, which will be equal to the total energy at the exit of the duct, which is CPTO2, and the total temperature. So this total energy can be written as CPT1, which is the internal energy plus kinetic energy of ρ1 u1 square equal to Cp T2 plus half ρ2 u2 square. And as this u2 is greater than u1, hence from this equation we can say that T2 has to be less than T1 to satisfy this energy conservation equation. Okay, so this will be the condition for supersonic flow in a divergent duct. Hence velocity will increase, which means Mach number will increase, and static temperature will decrease. So option B is the correct answer. By the way, this question was of 1 marks question. Second question, it is said that while flying at Mach number 2 at 11 kilometer altitude and producing same thrust, which is the correct order from the lowest thrust specific fuel consumption to highest thrust specific fuel consumption. So thrust specific fuel consumption TSFC is given as fuel consumed by the engine divided by thrust produced in F dot by T. Right now, for turbofan engine, so for a turbofan engine, the thrust produced by it is mostly comes from the bypass nozzle, right? So in that, no fuel is involved, no fuel is being added in that part, in the bypass nozzle. So and for that reason, the in turbofan engine, the thrust specific fuel consumption ratio is very low, because thrust is produced by the bypass engine where no fuel is being added. So this TSFC for turbofan is very low, perhaps the lowest for these three engines. So turbofan will have the lowest thrust specific fuel consumption ratio. Now, among turbojet and ramjet is mostly efficient for uh, Mach number two at the range of Mach number 2 to 4. And as the Mach number increases, the efficiency of ramjet increases. So in Mach number 2, for ramjet engine, the efficiency is very less. So for that matter, in ramjet engine at Mach number 2, the fuel it consumes is very high. So mf dot for ramjet will be very high compared to turbojet at same thrust. And and one more thing is that for turbojet is highly efficient at Mach number around 2. So for that reason, the ramjet engine around Mach number 2, the fuel it will consume is very high compared to turbojet, and that's why the thrust specific fuel consumption for turbojet will be less than the specific fuel consumption of ramjet engine, right? So the order of the TSFC for these three engines will be turbofan, then turbojet, then ramjet. So option B is the correct answer, and this is also 1 mark question. Next question. For a single stage subsonic compressor, which of the following statements about the highest possible compressor ratio is correct? Compressor ratio of axial compressor. So it's basically the options are a comparison of compressor ratio, compressor pressure ratio of axial compressor and centrifugal compressor. Now for centrifugal, for compressor, the pressure ratio, or perhaps the pressure increase across the compressor, can be given by this equation: dP by rho equal to d of omega square r square by 2 minus d of d square by 2. Now omega here is the angular velocity of rotor, r is the radius, and v is velocity, and of course dP is pressure rise across the compressor. Now for axial compressor, this R is constant, but whereas this in case of centrifugal compressor, this R varies. R is not constant. So in case of axial compression, this part becomes 0. So since R is constant for axial compressor, d of omega square r square by 2 equal to 0 for axial compressor, and hence this pressure rise is solely contributed by this uh, decreasing in kinetic energy of the flow inside the compressor. Whereas in centrifugal compressor, this r is variable, r is not constant. So in axial compressor, this pressure rise is solely contributed by reduction in kinetic energy. In kinetic energy of the fluid. But whereas in case of centrifugal compressor, the shape is like this. Right. So this is the inlet of the rotor. This is the outlet of the rotor, and so you can see that this radius of this rotor actually varying. So r is not constant for centrifugal compressor. Right. So in case of centrifugal compressor, this pressure rise is contributed by both of these terms. That is by d of omega square r square by 2 term, as well as d of v square by 2, which is reduction of kinetic energy. And that's why in centrifugal compressor, compressor pressure ratio is higher compared to axial compressor. Let me just brief this answer once again. So the pressure rise across a compressor can be given by this equation, which is dp by rho equal to d of omega square r square by 2 minus d of v square by 2. And this term is the reduction of kinetic energy of the flow inside compressor. And this term is contributed by the angular velocity and the radius of the rotor. Now, in case of axial compressor, as the radius of the rotor is constant, so this term becomes 0, and hence the pressure rise is solely contributed by the reduction of the kinetic energy of the flow, which is this term. But in case of centrifugal compressor, as you can see here, the radius of the rotor is actually increasing from inlet to outlet. So in case of centrifugal compressor, this pressure rise is contributed by both of these terms. And for that reason, the pressure rise in centrifugal compressor, or the compressor pressure ratio in centrifugal compressor, is more compared to axial compressor. And hence, this is the correct answer. Next question. For complete combustion of 1 mole of ethanol, the required number of moles of oxygen. So this is so one more question. So if we consider a stoichiometric mixture of fuel, that is ethanol and oxygen, the complete reaction of the this mixture will be, so taking stoichiometric mixture of fuel and oxygen the complete reaction would be C2H5OH plus O2 will give CO2 plus H2O. So if we solve this balance equation, the equation will come around something like this. So C2H5OH plus 3O2 equal to 2CO2 plus 3H2O. Hence, we can see that 1 mole of ethanol for complete combustion of 1 mole of ethanol, we require 3 mole of oxygen. Hence, the answer is 3. Next question. 1 kg of diatomic gas is heated and its temperature increases from 100 Kelvin to 600 Kelvin. The energy added at constant pressure during the process is 500 kilojoule. The specific heat at the constant volume of the gas is. So 500 kilojoule heat has been added and the temperature of the gas is increased from 100 Kelvin to 600 Kelvin. And we are asked to find out Cv. Right. So from energy balance equation, we can write that total energy added is equal to the increase of the energy of the diatomic gas. So Cp into increase of the energy of the and this is 1 kg. So 1 So total increase of the energy of the diatomic gas is mCp into 600 minus 100. This equal to total energy added, which is 500 kilojoule. So, and as m is equal to 1 kg, then Cp will be equal to 500 divided by 500 into 1. This kilojoule per kg Kelvin, which is equal to 500. Sorry, which is equal to 1. So which is equal to 1 kilojoule per kg Kelvin. Now we are asked to find out Cv, and we know that Cp by Cv is gamma, the ratio of specific heats at constant pressure and constant volume. And gamma is equal to 1 plus 2 by F, where F is degree of freedom of the gas. Right. Now for diatomic gas, this F equal to 5 for diatomic gas. That is, a diatomic gas has 5 degree of freedom. Okay, so gamma will be equal to 1 plus 2 by 5, which is equal to 1.4. So hence Cv will be equal to 1 by Cp by gamma, which is equal to 1 by 1.4. This will come something around 0.714 kilojoule per kg Kelvin. Okay. So this is the answer. Next question. A supersonic flow in a constant area duct at Mach number 1 encounters a ramp of angle theta 1. Okay. The resulting oblique shock with shock angle beta 1 is then reflected from the top wall. For the reflected shock, the turn angle is theta 2 and the shock angle is beta 2. And we have to find out which of these conditions is correct. Okay, so this is M1 incoming flow, and this encounters a ramp angle of theta 1. This is theta 1, and this this is the first oblique shock which is formed at this ramp angle at a shock angle of beta 1. So this is shock angle beta 1. So this is oblique shock, first oblique shock. Now this oblique shock is getting reflected from the top wall and forms a reflected oblique shock, which is second oblique shock. Okay. Now for this first oblique shock, this M2, which is Mach number of the flow downstream of the first oblique shock, must be less than M1, right? So M2 must be less than M1, as we know that across the oblique shock, a flow decelerates, the Mach number reduces. Now again, when this flow encounters the second oblique shock, at the downstream of the second oblique shock, the flow has to be parallel of the top wall, and this comes from the physical boundary condition of the flow. So downstream of the second oblique shock, the flow has to be parallel of the wall, right? So this is the wall. And the flow has to be parallel to the wall. So for this case, this is the deflection of the flow due to the top wall, right? Which is given as theta 2. Which is given as theta 2. Now, from geometry, we can see that as this and this are parallel, so this angle has to be equal to this, right? Because this flow is parallel to this wall. So from that we get from geometry that theta 1 equal to theta 2. Because flow at downstream of the first oblique shock has to be parallel to the bottom wall, and so this line is parallel to this, and this, so this angle has to be equal to this. So theta 1 equal to theta 2, and for the flow across this second oblique shock, so this is the second oblique shock. So the wave angle is this one, which is beta 2, right? So as we have got that theta 1 equal to theta 2, so we can conclude that this option and these options are not correct. Now we have to see the comparison between beta 1 and beta 2. So from the theta beta m relation, we can, so the theta beta m plot has been given, and we have discussed that m2 has to be less than m1. So this is for higher Mach number and this is for lower Mach number. So we can assume that this plot is for Mach number 1 and this plot is for Mach number 2, right? And as we have seen that for both the deflection, theta deflection angle will be same. So for same theta, this this will be beta 1, right? And this will be beta 2. for same theta, the higher Mach number produces lower shockwave angle, and lower Mach number produces higher shockwave angle. Hence, from this plot, we can say that beta 2 is greater than beta 1. Hence, option D is correct. Right? Okay. Next question. In a turbojet engine, the compressor outlet temperature increases with decreasing efficiency of the compressor. If the turbine inlet temperature remains constant with decreasing efficiency of the compressor, the thrust specific fuel consumption of the engine. Okay. So it is being said that the turbojet compressor, so if the compressor efficiency eta C decreases, then okay, so first let us draw the TS diagram of the turbojet engine. Okay, so this is the entry of the engine. This is exit of the outlet. This is exit of the compressor. This is exit of the burner or combustion chamber, and this is exit of the turbine, and this is exit of the nozzle. Okay, now this dash denotes the isentropic process. So in case of this part is compressor and this part is turbine. So as eta C, that is the compressor efficiency, decreases, the compressor outlet temperature, that is TO3, increases. Right, TO3 increases. Now the total power required to run the compressor is Cp TO3 minus TO2, and this power is contributed by the power produced in the turbine, right? So this is the power required to run the compressor, and power produced by turbine is TO4 minus TO5, and it has been given that TO4 is constant. So if this is, so if eta C decreases, TO3 will increase, which means the power required to run the compressor, which is WC dot, will increase. And as this power is solely contributed by the power produced by the turbine, which is WT dash, hence in case of if eta C decreases, turbine has to produce more power, right? And as TO4 is constant, so to produce more power, which means to increase WT dot, TO5 has to decrease. So if eta C decreases, TO5 will decrease, right? Now if TO, and this TO5 is the nozzle entry temperature. So, and in nozzle, the total energy of the flow at the entry is CpTO5. So this will be nothing but CpT6 plus half into Cj square, where Cj is the exit velocity, the exhaust velocity of the nozzle. So if TO5 decreases, this Cj will also decrease, which means the thrust produced by the engine will decrease. And as the specific fuel consumption so Cj will decrease, which implies that thrust will reduce. That means the specific fuel consumption, which is MF, so specific fuel that is MF dot by T, the thrust specific fuel consumption. So TSFC equal to MF dot by T. So as thrust reduces, so TSFC, thrust specific fuel consumption, will increase. So the correct answer is the thrust specific fuel consumption increases as the compressor needs more work input from turbine. Right. Now one more thing, here as TO3 increases with decrease of eta C, and as TO4 is constant, hence in the as eta C decreases, we will be requiring less fuel to get same TO4, right? Because TO3 is increasing. So in a way, when efficiency of compressor decreases, the fuel consumed, that is MF dot, will also reduce. MF dot will reduce, but the reduction MF dot, and if MF dot reduces from this equation, you can say TSF should reduce. But there is one catch here. The reduction of TSFC due to reduced MF dot will be much less compared to the increase in TSFC due to reduced thrust. So which means due to reduction of thrust, the increase in TSFC will surpass the reduction of TSFC due to reduced MF dot. So overall, we'll get increased thrust specific fuel consumption ratio. And the reason of that is that to run the compressor will be requiring more turbine power, which in turn leads to reduced thrust. So option C is the correct answer. Next question. Static pressure ratio across a stationary normal shock is given by this equation. Now M1 is the upstream Mach number for a stationary shock in air. With upstream flow condition given by speed this, static temperature this, static pressure this, the static pressure downstream of the shock is okay. So for a stationary normal shock, the ratio of the pressure across the shock is given by this equation, and the upstream conditions of the flow has been given, and you have to find out the static pressure at the downstream of the shock. Right. So this is the normal shock, and this is the, so this is 1 and this is 2. 2 is the downstream condition, 1 is the upstream condition. So here U1 has been given as 800 meter per second. And E1 is 1 atmosphere, and T1 is 300 Kelvin, and we have to find out T2 from here. So from this equation to get P2, we need the value of M1, right? We need M1, and M1 is nothing but U1 by A1, which is U1 by root over gamma R P1. Now substituting all these values, it is 800 divided by 1.4 multiplied by 287 multiplied by 300. So this will come around 2.304. Now we just have to substitute this value at this given equation. So from that we get P2 by P1 equal to 1 plus 2 into 1.4 by 1.4 plus 1 multiplied by 2.304 square minus 1, which gives P2 by P1 equal to 6.026. So P2 will be nothing but 6.026 into P1, and P1 is 1 atmosphere, hence P2 will be this into 1 equal to 6.026 atmosphere. This is the answer. Next question. So this question is from rocket propulsion. So it is said that for a rocket engine, the velocity of the velocity ratio R is given by VA divided by VE, where V is the vehicle velocity and V is the exit velocity of the exhaust gases. Assume the flow to be optimally expanded through the nozzle for R equal to 2, the thrust produced by the rocket, and then a dot is the mass flow rate of exhaust gas, then F by M dot VE is okay. So for a rocket engine, we know the thrust produced by a rocket engine. Okay, thrust produced by a rocket engine is, so it can be given by F equal to M dot VE, where M dot is the mass flow rate of the exhaust gases, and VE is the exhaust velocity. So we can see that this thrust equation of thrust is independent of the vehicle velocity. So thrust is thrust produced by rocket engine is independent vehicle velocity. So it doesn't depend on the ratio of the vehicle velocity and the exhaust velocity. So F by M dot VE, from this equation you can say this will be 1. This will always be 1 irrespective of the vehicle velocity. So this will be 1. Next question. The specific impulse of a rocket engine is 3000 Newton second per kg. The mass of the rocket at burnout is 1000 kg. The propellant consumed in the process is 720 kg. Assume all factors contributing to velocity loss to be negligible. The change in vehicle velocity delta U is, okay, so again this is a question from rocket propulsion. So we know that for rocket propulsion, the change in burnout velocity, the change in velocity delta U is Vj into ln of initial mass of the rocket, which is mi divided by final mass of the rocket. which is mf. Now Vj is the exhaust velocity of the rocket. Now mf is the final mass of the rocket is 1000 kg, and initial mass of the rocket equal to final mass of the rocket plus the mass of the consumed propellant, which is this. So this is 1000 plus 720 1720 kilo. So and Vj is equal to 3000 meter per second. So delta U will be 3000 multiplied by ln of 1720 divided by 1000. This meter per second, which will come around 1626 meter per second, or 1.626 kilometer per second. This is the answer. Next question. The combustion product of a gas turbine engine can be assumed to be calorically perfect gas with gamma 1.2. The pressure ratio across the turbine stage is 0.14. The measured turbine inlet and exit stagnation temperatures are this. Respectively, the total turbine efficiency is. Okay. So the TS diagram across the turbine will be like this. So this is the entry of the turbine. It can be denoted as O4, and this is exit of the turbine, O5, and this is exit of the turbine for a isentropic case. That is, if the turbine is ideal, that is reversible adiabatic, then in that case this will be the outlet temperature of, this will be the outlet condition of the turbine. So from this, now the turbine efficiency, eta T, the total to total turbine efficiency, is denoted as is written as TO4 minus TO5 divided by TO4 minus TO5 dash. So actually this efficiency is written as the change in enthalpy across the turbine in the across the turbine, and divided by change in enthalpy across the turbine in ideal case. So this eta T is actually HO4 minus HO5 divided by HO4 minus HO5 dash. Now as Cp is constant, so this can be written as TO4 minus TO5 divided by Cp TO4 minus TO5 dash. So Cp will get cancelled, and this will lead to this form, TO4 minus TO5 by TO4 minus TO5 dash. Okay. Now, so from this equation, let's say 1. So from equation 1, eta T is TO4 1 minus TO5 by TO4 divided by 1 minus TO5 dash by TO4. Now, so TO4 gets cancelled, and this TO5 dash is the total temperature at the exit of the turbine for isentropic case. So TO5 dash by TO4 is can be given by pressure ratio across the compressor, that is PO5 by PO4 to the power gamma minus 1 by gamma. So this is isentropic relation of gas, right? So if we substitute, and PO5 by PO4 is given as 0.14, which is nothing but 0.14 to the power gamma is 1.2, hence 0.2 divided by 1.2. If we substitute this here, and TO5 is given as 1200 Kelvin. Okay, so TO5 is 1200 Kelvin. TO4 is no, sorry. So TO4 is 1200 Kelvin, and TO4 is 1200 Kelvin, and TO5 is 900 Kelvin. So if we substitute all these values here in this equation, eta t, we'll get eta t, and it will come something around 0.8947, which is equal to 89.47%. Hence it will be 89.7. This is the answer. Next question. The figure shows the velocity triangle for an axial compressor stage. The specific work input to the compressor stage is okay. So the velocity triangle is given for a flow in an axial compressor, and you have to find out the specific work W. Okay, so this is the entry of the compressor stage. So this angle is alpha 1, this angle is beta 1, and this is exit of the compressor stage, and this angle is alpha 2, this angle is beta 2, right? And Cz is constant throughout the compressor, axial compressor. So Cj will be constant, and we know that for axial compressor, the formula of work output, formula of work input to the compressor stage is given by U Cz by tan alpha 2 minus tan alpha 1. Right. Now E is this peripheral velocity. So this alpha 1 is given as 30 degree, and alpha 2 have to find out. If we see this equation, this triangle ABC, tan alpha 2 is can be written as BC divided by CA. So and B, this is 40 meter per second, and the total peripheral velocity is 100 meter per second. So this will be 60 meter per second. And as Cj, that is axial velocity, is constant throughout the axial compressor, so AC will also be 60 meter per second. So from this we can write tan alpha 2 equal to 60 by 60, which is equal to 1. Means alpha 2 is 45 degree. So substituting this value, this value and the value of U and Cz in the equation of work input, we get 100 multiplied by 60 tan of 45 degree minus tan of 30 degree. So this joule per kg, right? So it will come around 2535.89 joule per kg or 2.535 kilojoule per kg. So this is the answer, 2.535. Okay, so these were all the questions from gas dynamics and propulsion, and we have discussed the solution of the questions. Thank you.